So welcome to today's Fireside Chat. We have Nathan talking about Serde Deserializers. I will just go ahead and pass it off to Nathan and let you go ahead and get started.
Yeah, thanks, Ricky. Yes, I am Nathan West. I am a senior developer here at 1Password. And today I wanted to talk about Serde Deserializers. This came up for me recently just because I got attached to a project called KDL, which is basically like XML, but pretty like YAML. And I started writing a deserializer for it, and I got really interested in how it all works. And then we make a huge amount of use of it here at 1Password. A lot of the messaging between our various components in our new core apps uses Serde for that sort of stuff. So Serde, what we talk about Serde. Serde, for those who don't know, is a Rust library that is how Rust talks to wire formats, right? So if you're talking to JSON or YAML or XML or more binary formats like MessagePack or even like TCP packets. It's a way to interchange between those wire formats and Rust data in a very efficient way that doesn't involve going through a lot of intermediary data structures and a lot of intermediary allocations and so on. I sort of got lost when I was playing this talk, trying to figure out how to sort of structure it, because Serde can get very complicated. There's a lot of traits, there's a lot of types, there's a lot of complexity that you can run into. But at the same time, Serde is highly misuse resistant. It's probably the best example I know of a really solid misuse resistant library. And what I mean by that is that the way that it sets up its types and its traits makes it very hard to do the wrong thing, because you just don't have the APIs that you would want to do the wrong thing. This leads me to the only point that I actually really want to make about Serde. This is the point. When you're lost, when you're using Serde, if you're getting lost, if you're in doubt, just follow the types. Just as an example, here's a deserializer trait. We'll be going into what this means more when I get into like the code examples and everything. But for now, just look and see that we have a method here, deserialize string. Okay, it takes a visitor v and it returns v's value, right? So already we are sort of limited in what we can possibly do, right? We don't know anything about v's value. Presumably the visitor does. We know about our own error type. But if we want to return something from this function that's not an error, we have to go through the visitor. Okay, what does the visitor look like? It has this sort of the same method in reverse. It has a method called visitString that returns its value, right? The only possible way, because this value doesn't have any traits, it isn't default, it isn't clone, the only possible way you're going to get your hands on a visitor's value is by calling the visitor's method, visitStir, which will return a value, or it'll return your error, right? Conversely, the visitor's function here is generic over error. So the visitor doesn't know anything about the error except that it implements this error trait, which we'll see has a bunch of constructor methods and so on that allow visitors to create their own errors. This pattern is pervasive. We're going to see a lot of types, but they always sort of go in this pattern where it's some kind of function and it returns some kind of value, but there's only one specific way you can never put your hands on that value, which means you have to go through the interface that Serde is providing for you. Sticking to this principle is going to resolve a lot of your confusion, and it's going to help you sort of take yourself on a guided tour through the whole thing. All right, cool. The only thing I need to talk about before we just go right into the code examples is the Serde data model. The way that Serde works is that it has this idea that all data in the world that it cares about can fit into this data model. So all data coming out of JSON or coming off your wire, all data in Rust, like your structs and your enums and your primitives and everything, all fits in this data model. So what do we have in the data model? We have the classic primitives. We love these: ints, bools, characters, floats, unit types like empty tuple and empty structs and that sort of thing. You know, pretty basic, not much to say about these. Strings and byte arrays, pretty similar to primitives, but there's some cool stuff that Serde does with borrowing that we won't be getting into, but suffice to say that they do some cool stuff with this, where you can get some really cool zero copy deserializing going. We have option. We're going to see later that Serde does have enums, but because null is such a overwhelmingly common type of thing, you might like in JSON. JSON has null. YAML has null, right? Every format has a null. And so Serde has a specific special case for handling optional data. And finally, the structured data types, right? So these are all containers for other Serde values, usually highly heterogeneous, right? You can just put whatever you want in these containers. We have sequence types, right? These are your vectors, these are your tuples, everything that's just a bunch of things in order of whatever type you want, right? You can have sequences of sequences, you can have sequences of ints, you can have a sequence of an int and then a sequence, however you want to do it. We have map types, same thing, but they're key value, right? Keys can be anything, values can be anything. There's no idea of key equality or value equality or hashing or anything like that. It's just a list of pairs. We have struct types. Struct types are basically the same as like a sequence type or a map type, but they also come with a type name and a list of all the fields that you might see in the struct, which the deserializer might want to use to inform how it behaves. And enum types. Same thing as the struct types. They are similar to the other structured types, but they include a type name and a list of all the variants that it could possibly be. Now, what's interesting about this data model to me is that it can at many times be both a super and a subset of what a particular wire format can do. We're going to be for the bulk of this talk writing a CSV deserializer from scratch, which is going to be a lot of fun. But you'll notice that a lot of this stuff isn't really applicable to CSV. CSV, especially the way we're going to be doing it, does not have this idea of an optional. It doesn't even have an idea of a number, right? We're just going to do a list of strings. JSON doesn't have a built-in notion of an enum, et cetera, et cetera. A lot of the interesting work that Serde does and a lot of the ways that it's designed allows you to be flexible about this, right? If you're using a format that doesn't support ints, which we are going to be, you just return an error if the type asks for an int, and so on and so on. Cool. Are there any questions already? We're only 8 minutes in, but are there any questions so far about anything I just said before I jump into writing a bunch of code? Seeing heads being shaken. Excellent. All right. So, like I said, the way that we're going to do this is we're going to follow the types. And what we're going to do, like I said, we are going to write a CSV deserializer pretty much from scratch. CSV, I'm sure you all know, looks like this. It's just strings separated by commas, separated by lines. We are not going to be doing any interesting parsing at all. We're not going to be doing quotes. We're not going to be doing escapes. This is going to be purely separate on new lines and separate on commas and go from there. Just because the work of parsing is not really relevant to how deserializers specifically work. All right, so let's think about some of the types. I have here a Rust module, right? It's got this main function that we'll be doing in a minute. And then by convention, deserializer stuff goes in a submodule called DE. So we're just going to jump right into it. We're going to make a deserializer, struct deserializer, deserializer. All right. We're going to read from files and other types of IO data. So we're going to say we have our input. It is a reader. We'll say this is an IO buff read. Great. And the other thing we're going to say in here, there's basically two kinds of CSV files. Sometimes they have these headers and sometimes they don't, right? We are going to use these headers to produce structured data, right? If a data type wants to be serialized as a map or as a struct or something, it wants key value pairs. So we are going to use this as a key and this is a value, and then this is a key and this is a value, and so on and so on. Or maybe there's no header, in which case we just are going to produce lists of strings. We want to do either one, so we are going to actually configure it to do that. We're going to say headers is a bool. All right, great. We'll go ahead and write we'll make this public so we can get to it later. All right, great. So this is a deserializer, so it should implement deserializer. Let me go ahead and grab one more import. We're going to use Serde DE. The convention that a lot of implementers use that I really like is rather than implementing stuff from DE, like importing these traits and everything, we just leave it here DE and we scope it this way. It helps because you have like DE error and DE deserializer. It helps to keep Serde's stuff separate from your own stuff. So we're going to implement DE deserializer for our type. You notice that I haven't really talked about what's in this trait yet, and that's by design. When I was doing this for the first time several weeks ago, this is basically how I did it. I sort of knew at the time that there's this follow the types premise, and so you can just sort of go from the back forward. There is a lifetime on this trait that we don't really care about. This is the deserializer lifetime. This is the lifetime of all data in the deserializer. This is what allows you to like deserialize strings without doing any copying and just sort of borrow the string right from the input. But because we are using a IO, we're using a reader object, this is never going to be relevant to us. We have to put it here, but we're going to be ignoring it all the time. All right, let's fill in this trait. What's in here? Unfortunately, it's a lot. You can see on our map here, we have created several dozen methods here. There's a shortcut that we're going to use to clean a lot of this out. But notice that this is basically the entire data model, right? These are all ways that a type can ask for data, right? I'm asking for an I8 or an I32, or I'm asking for a string, or I'm asking for a new type struct, right? Whatever it might be. Now the trick that we're going to do here, we're going to notice that a CSV file is always a list of something. It's either a list of lists or it's a list of maps. It is never a string. It is never anything else than a list of something. What that means is that we can use deserialize any. We can say that no matter what we are asked for, we are always going to give you a list. And if you don't want a list, you can create the error and give it back to us. But we are going to give you a list no matter what. The shortcut this enables is that we can get rid of all of these methods, get rid of them all. And Serde provides a macro that says forward everything that we didn't implement, forward it all to any. So I'm going to grab this over here. We're going to put it right here. Okay. All this means is that each one of these is attached to one of the functions that we just deleted, and it just means call deserialize any. Easy. All right. First things first, we need an error. All right, let's go ahead and make an error. We're going to be using this error to make our lives much easier for implementing this thing. We're going to say this is a debug object and it is an error object. We'll go ahead and use this error. Cool. Say this is an error. This does not belong here. That's a good point. Thank you. Let's put this over here. Great. All right. First thing it's yelling at us about is that this needs to implement a trait called de error. All right, let's go ahead and do that. Impl de error for error. Fill some of this in. This is a constructor, right? It's easy, right? Create this error. Here's a message. The message is display. It can be turned into a string. There's a bunch of other methods here that are default implemented in terms of custom that we can fill in if we want to, but we're not going to bother. We're going to do the simple thing and just do custom. So we'll say this is a custom error. It's got a string in it. We will say there's an error message here, which is error from deserialize type. And we will say this is going to return an error custom of message dot to string. Great, easy. All right, done. All right, let's fill in this method here. Oh, did I copy the wrong one here? So give me just a second. I grabbed the wrong paste from this. That's my fault. Great. All right, let's start deserializing something. Well, what do we want to do? We know we want to deserialize a list of something, and we know that in order for this method to work, it has to return a value, a v value, which means that our only choice is to do something with this visitor. This is what I mean by follow the types, right? So we're going to look at a visitor. We're going to say visitor dot, and we're going to see that we can visit all these different types. All these methods are how we send data into the type that we're deserializing. So for example, if we want to visit a bool, we can see, all right, this method takes a bool, right? So we have a bool value, we send it into the data. What we have in this case, though, is a sequence. So we are going to visit a sequence. Visit sequence. Great. All right. What are we going to pass into a sequence? It's probably not a vector because we know that this is a very low overhead crate. So we're going to look at this and we're going to see, oh, it's anything that implements sequence access. This is where the follow the types thing sort of gets really interesting, right? We were called with this, right? Some type asked us to be deserialized, and it provided us a visitor. It said, I am capable of receiving data into this visitor. In return, we're going to go back to that and say, all right, here's a sequence. I'm going to provide you with a sequence access that you can then use to extract all the data you want. So let's go ahead and make one. We're going to make a struct. We're going to call this a rows sequence access, because this is how we're going to get all the rows out of our data. You'll notice that pretty much all these methods take self by move. A lot of sort of production deserializers will impl for mutable self to make this equivalent to a mutable self. I actually really like the by move form though, because it creates a very sort of obvious contract where one deserializer object gets turned into one CSV document. And we're going to see later, one deserializer object gets turned into one row, and so on and so on. It's sort of a nice little dance that happens. So we gotta make a seek access. Let's put some data in here. We know we're gonna still need our input from earlier, the file we're reading from. So R is an IO buff read. And we're gonna do some headers. So this is now actually a really good point to do our headers thing, right? While we are setting up this visitor, we are also going to take the opportunity, if headers is true, we're going to start reading from our reader to produce a list of headers that our downstream types are going to be able to use to produce our structs. So we will say we want headers, and we say this is going to be an option of vec of string. Easy. We will go ahead and put one. We'll go ahead and put it together. We will say if self.headers, and we will say we actually do this. Let headers equals this. All right. Let's start reading data off of our reader. We're going to make a very easy helper function for this because it's going to be the same thing basically every time. We're going to make something called read CSV line. This is going to be sort of the extent of our parsing, quote unquote, because this is going to be where we split on new lines, and it's going to be where we split on commas. All right, so we've got a readable object, buff read, and we're also going to send it a buffer as an argument, because we're going to want to be reusing this buffer every time we read a new line. So what we're going to say is there's some buffer lifetime. Here's a buffer. And we are going to return, all right, it's got to be an IO result of something, because if we try to do a read and nothing comes out, that's bad. So we're going to do an IO result of something. And it needs to basically be, it's functionally an iterator, right? If we find an empty line, then the document is done. If we don't find an empty line, that's great. We split it on commas. So we'll say this is going to be an option. And what's going to be in here is actually an iterator, right? We're going to say, if we found a non-empty line, give us an iterator of the strings we found in this line, which we can later turn into strings or send to the deserializer or do whatever we want to. There's no reason to do any stringification this early in the process. So buffer lifetimed, impl iterator item is a string. Cool, let's implement it. It's not that difficult. We're going to say buffer.clear. We are going to say input.read line into the buffer and return an error. We're going to take off the trailing new line. I'm going to say buffer equals buffer.trim and matches on the new lines. And finally, if this buffer is empty, if not empty, excuse me, we are going to return our iterator. Otherwise, we're going to return none. So we'll say match buffer.isEmpty. If it's not empty, cool. Buffer.split new line. Otherwise, no. Let's use the right names for things. Let's make it mutable. It is mutable. What's going on here? Oh. Oh, I see. This needs to not be like this. There we go. All right, so simple parser. It turns out that you can't really fail to parse a CSV file. All input strings are technically valid CSV documents because it's just the rows can be variable length. It's actually pretty funny. All right, so let's read a line. If we got some headers, we're going to say let line equals read CSV line, read CSV line. We have our input. Let's make a buffer. Cool. If something goes wrong, let's return an error, which means that now we have to actually think about, let's add an error case for this. We got an IO error. IO error. Cool. We're going to say IO error during deserializing. We will go ahead and put a from in here, which makes the question mark work. Great. All right, we've got our line. It's an optional iterator. If this is none, that's a problem, right? We needed headers. There's always going to be at least one line in the CSV document with headers. We need to have the actual headers. So we are going to say match line. If it's none, we're going to return an error. A lot of this can be done with combinators, and I might clean it up later, but it's sort of easier to talk through in the less combinated version. We are going to return an error, and we need another error case. We're going to say missing headers. There were no headers in the document. Cool. We will return this. Return error, missing headers. Otherwise, we have our line, some line. Cool. We are going to turn this into a vector of strings because we need to keep it around for the entire span of deserializing the rest of this document. So we'll just go ahead and say line dot map s.to owned dot collect. Easy. And finally, if the headers bool was false, if we didn't ask for headers, the whole thing needs to be done. So we're going to say else none, and up here we're going to make this a sum. All right, we have our headers. It's an optional list of strings. We will go ahead and put it in here. We're going to actually pass this here. Row seek access. Input is our input. Headers are our headers. And we have this great buffer. We're going to keep this around so that we can keep reading lines into it so that we don't have to keep allocating every single time we read a new line. We'll say we have a buffer, which is a string. And we'll pass that in here as well. Great. All right. This is now yelling at me, very obviously, that we have not implemented this trait on this type yet. All right, let's hop to it. Impl de sequence access for rows seek access. This needs to have the lifetime on it. This will do the lifetime, and here's our reader type. All right. Just like before, we're going to fill in missing members and see what it wants from us. We're going to follow the types. It wants an error type. Generally, we want the error type to be the same throughout this whole process. So we're just going to keep using the error type we already have. All right, and we have next element seed. Well, what are we doing here? We are returning a result of an option, which sort of makes sense, right? Because something can go wrong during deserialization, or because we are deserializing a sequence, we're going to keep returning sums until we return a none, right? This is just an iterator interface. But what we return is a t value, and t comes from this deserialized seed trait, right? So once again, our only choice to succeed at this method is to do something with this seed. So what do we do with it? Well, we know that we know that we want a row. Before we do anything with the seed, we know that we are going to want a row. So let's go ahead and get a row. Let's say let row equals buffer, or sorry, read CSV line from our input using our buffer, and possibly returning an error if something went wrong. All right, we have an optional iterator. This option and this option end up being pretty much the same, right? If this returns none, there's no more lines in the document. This is a none. There's no more elements in this deserializer. We can stop deserializing this sequence, which means that we can very easily map this. So dot map. Here's our row. All right. What are we doing with it? Well, we have our row. We don't know what to do with it yet because we don't know what the seed wants. Let's go see what the seed wants. Seed wants to deserialize something. And it wants a new deserializer. So this is interesting, right? So we know that the deserializer type is the type that can produce data. Like we are writing a deserializer for an entire CSV document. This is now asking us for another deserializer for the individual row. Well, all right, we got to go make that. It's funny because like I can sort of hear I can hear as I am stacking up more and more things. Right. This is where it gets very interesting and complicated, and this is where the challenge comes in trying to write slides for this and trying to cover all this information. But it's sort of you're sort of working with Serde. You're just doing what it wants you to do, and you're following the types that it's asking you to follow. Let's make a row deserializer. Row deserializer. All right. What's in here? Well, we need several rows, so we're not going to own our input. So we'll go ahead and borrow that. We will say our input is a I'm sorry, we don't even need that. I take that back. We already read our data here in read CSV line. We no longer need access to this reader. All we need access to is this row. All right. So we have a row. A row is an iterator of strings. So we will say I is an iterator of strings. Cool. What else do we need? We need the headers, right? If this row wants to be turned into a struct, it needs its own row and also the header row so that it can pair off individual items to create key value pairs. So we'll give it some headers. We will say this is a borrowed slice of strings because we're going to get this borrowed slice. We're going to get this borrowed slice right from our vector. And that's pretty much all we need. So we're gonna use this. We're gonna say here's the deserializer that we're going to use. We're gonna put it right here. We're gonna put some stuff in it. Here's our row. Here's our headers. We're gonna say headers is we're gonna go ahead and borrow our headers. Self.headers.as deref. Great. All right. Now deserialize can return an error, right? So what we have here at this point is an option that we are mapping. This can be an error. We have an option of an error. We want we have an option of a result. We want a result of an option. It's a rare opportunity to use transpose. We love it. Let's go ahead and use self. Let's actually use the right things here. Self.input, self.input and self.buffer. This is optional, right? We don't know if we have headers. We'll make this optional. Cool. And this is just saying we don't have the trait implemented yet. So we'll go ahead and do that. Let's go another row deeper. All right, we have a row deserializer. So whereas before we had a deserializer that was just for an entire document that turns a whole document into a list of something, now we have a deserializer for a row that's going to turn a row into probably a list of something. So let's go ahead and say impl, here's our borrowed lifetime, here's our deserializer lifetime, here's our iterator, de deserialize for row deserializer, oh sorry, deserializer. Where I is an iterator of strings. All right, so we're going to fill this in. We're going to see it's going to give us a 1,000 or so methods. But once again, we're going to use this macro trick to clean it all up. We're not going to clean them all up though. I'll get back to why in a minute. But well, we'll clean them all up for now actually, and then we will revisit that decision and see why we can do something more interesting here. All right. So once again, we know that a row deserializer always turns into the same thing. What it turns into depends on the headers, right? If we have headers, we are deserializing a map of key value pairs. If we don't have any headers, all right, we're deserializing a sequence of just whatever was in this row. So let's go ahead and do that. We'll say match self.headers. All right. If there were no headers, we want to visit a sequence, right? We have our visitor again. The visitor is how we send data in to the type that is asking to be created. So we're going to say visitor dot visit. We're going to visit a sequence here, just like we did before. If we did have headers though, well, now we want to visit a map, right? Visitor dot visit map. which has a very, very, very similar API, but instead of having this sequence access, which just produces elements, it's going to have a different trait that produces key value pairs that we'll see in a second. All right, so we'll do the easier one first, which is this handling a sequence. Let's make a row sequence access. Struct row seq access. Just like before, we have our iterator of strings. We know at this point that there are no headers, so there's no reason to put anything else into this type. We'll say this is an iterator of strings. Cool. We will put this right here. We will say that row is self.row. Cool. We will put this as an item. Great. It wants a trait. All right, let's do a trait. We will impl seek access for our row seek access of our lifetime and our iterator. Okay. We already saw this interface before. It has this error type and it has this next element seed, which just produces the next element. Great. Well, a row is a list of strings, right? A list of cells. So that's what we're going to do. Luckily, we don't have to make any more types for this because at this point, Serde starts to help us because it has basically some very simple helper types to do trivial deserializations like this one. We want to just deserialize a single string into something. What we're going to do is we are going to say self.row.next, right, as an iterator. We know how to use iterators. .map, if we found an item, that's great news. We're going to feed it into our seed.deserialize something. We needed a serializer. So previously we had to write our own deserializers because we were doing complex stuff with our specific data format. But this is just a string, and it turns out that in this module is a trait called into_deserializer, item.into_deserializer. This just says this is a string. Turn this string into a deserializer that always deserializes a single string, right? We don't have to deal with writing another one of these things. It takes care of it all for us. This looks like an option of a result. We want a result of an option, so we will once again transpose it. We will use the error here. And we're done. That's it. That's it for rows, at least. The last thing we need to do is this other half, maps. So this is now, we do have headers. So let's make a struct map access, struct a row map access. I forgot how to write syntax. There we go. So just like before, we have our row, but this time we also have some headers. This is a list of strings. Beautiful. Let's go ahead and use it. Let's put it right here. We have our row map access. It wants our row, and it wants our headers. Our headers are just a slice of strings, so we're going to be just reusing this. It's cheap to copy. We're just going to be using the same slice of strings over and over and over again for every row that we want. Oops. Great. It wants this trait row map. It wants this trait map access. All right, let's oblige it. Map access. We'll grab this one more time. Our interface here. Cool. All right. Now, what does a map access look like? I'm going to tell you it looks very similar. So instead of having just next element, it has next key and next value. The reason it splits next key and next value into two methods instead of just having one method that is, get entry with a pair is that when you're deserializing a structure, it might want to pick a different type with which to call next value seed, right? If you're deserializing a structure that has a string and an int, it's going to want to know what the key is so they can pick the right deserializer to feed into next value. All right, we have our error. Error hasn't changed at all. All right. So the way we're going to do this, one option would be to pluck a header off the headers row, return it here, and then pluck an item off the row itself and return it here. But that makes it so difficult to track certain cases, like if the row is too long, if the row is too short, and we want to deal with all that at once. So we're actually going to do all that right here in the key. So we are going to get a header. We're going to say headers self.headers.split first. And we're going to get an item at the same time, row.next. All right. What can we have here? We can have a new item. Great. We got our, we have our header and our tail. And we have our row. This is the best case scenario, right? We have a header, we have a tail. We will go ahead and save the tail. We'll say self.headers equals tail. This is like the remaining headers in our list of headers. We need to save the item that we found. Oh, this needs to be some item. There we go. I'm sorry. We need to save this item because we actually don't want to return it until next value. So we're going to put a quick little thing in here. That's just next item is an option of a string that we got from the iterator. And we will go ahead and save that. Self.next item is some item. Cool. And finally, we're going to return our header. Our header is literally just a string. So we do the same thing we did here. We turn a string into a deserializer and feed it into the seed. So we will say we will say seed.deserialize. We will feed it our item.asString as stir. I'm sorry, excuse me. Feed it our header. That's the first part we need. Our header.asStir into deserializer. Wrap it all up in a sum. Great. What else can happen? Well, if we return a pair of nones, that's fine. We're done. Great news. So we were going to go ahead and return okay, no. Cool. And then some other things can happen. Right here is where you can get really sort of fun with error handling. This is where you want to start recording like line numbers and column numbers and specifics about what went wrong. In this case, we're going to do a very simple thing. We're just going to say we had a row length mismatch. And we're going to say this this occurs when row was a different length than the headers. Cool. Yeah. So in a real CSV parser, you might want to record more specifics about what went wrong here, but for now, we are just going to do this. So if something else happens, that's an error situation. We're going to return mismatch. We are going to do self.row. That's important. All right, great. And finally, we need our value. This is the easiest one ever. The value is fun because it's allowed to panic, basically. If the caller calls next key and next value out of order, like it calls next value twice or something, this is allowed to return garbage results. It's not allowed to do unsafe things, but it's allowed to panic or hang or do whatever you might want to do. So this is our easiest one ever. We're going to return okay. We definitely have an item. It definitely lives here in next item. Okay, next item. Oh, I'm sorry. We don't return it yet. We have our item, but like usual. So actually, let's do it. Let me try to do what I just tried to do because it's a cool mistake that I just made that it's going to demonstrate the point that I'm trying to make. So what I just tried to do was return this string, right? Expect called next value seed out of order. So my instinct was, all right, we have our item, let's return it. This is going to fail though. It's going to say we have a mismatch type, right? We don't return strings from this function. We return a v value from this function. And we know nothing at all about v value. It doesn't have any additional trait bounds on it. All we know is that seeds can make them. Whatever it is, a seed can produce a value. So the only possible way to make this function compile and do the correct thing, besides just returning an error unconditionally, is to ask our seed to do something. So let's try to do it correctly. We have our next item from before. We will say seed. We have our next item right here. Well, let's go ahead and do this. Let item equals it. And then we will say seed.deserialize item.into deserialize. Now it compiles. Right now it's happy because we have fulfilled these type constraints. Cool. That's it. This is less than 200 lines of code, and it is an entire fully functional CSV parser that we will see in just a moment, assuming I didn't make any mistakes. We have a new field here. That's fine. Next item is none. What else went wrong? Self needs to be mutable in order to borrow this as immutable. All right, that's fine. Cool. We have some unused imports, which I'm happy to get rid of. All right. Yeah, that's it. The very last thing I want to do before we go back to our main and start playing with it is that I'm going to put a constructor on this type so that we can start using it. Assuming I can find it. Where is it? Here we go. We will go ahead and put a we'll say we have a new function here. Actually, we'll do two. We'll say new with headers with our input. And we'll say, let's make it public too, so we can use it. And we'll say new without headers. Cool. We don't want this. That's going to conflict with us. Great. All right. Let's go try it. So I took the liberty of producing some very simple CSV data here that we're going to be trying. Here's a very simple struct, right? Name, description, value, direction, data, some strings, a number, and a direction, and some other ones that we'll see in a minute. So this is our data. It has these 4 fields. We're going to ignore the last 2 for a second. We're going to do just name and description. So how do we fetch this, right? So now that we're done running our deserializer, we are now sort of back in regular old Serde land. We're going to make our struct, right? This is our classic. It's our favorite thing to do is derive deserialize on things. We're going to use Serde deserialize. Here's our data. It's got a name, which is a string, and it's got a description, which is a string, right? This is the pattern that we're all very used to from like, JSON and that kind of thing. Okay. I'm going to take a minute to talk a little bit about what derived deserialize here does. This is going to create a trait implementation on this type that uses this uses this interface. So, earlier we said that somebody has to call deserialize any with a visitor. Well, that's what the deserialize implementation does, right? So this implementation of deserialize is going to create a visitor specific to this data struct. It's going to feed it into this method, and everything we just wrote is going to sort of percolate down from there, because every single type has a every relevant type has a deserialize implementation that produces a visitor that's capable of receiving data that type runs, right? Like an integer has a visitor that receives numbers. A string has a visitor that can receive different kinds of strings, and so on. All right, we are just going to read from stdin, the easiest thing in the world. We're going to say let stdin equals io stdin, let mute stdin equals stdin dot lock. Let's go ahead and make our deserializer with headers using stdin. And let's use it. All right, so we know, like we said earlier, a CSV file is a list of rows, right? So it's a list of something. So we're going to produce a vector of data. We're going to say a let value is a vector of data equals vec deserialize from the deserializer, right? This method is going to take this deserializer and it's going to call whatever method vec wants to get data from. We're going to do some error handling here. So we're actually going to use anyhow to get some pretty errors from this in case anything goes wrong. We will say dot context on this, deserializer error, return it. If we got something though, let's print it. Hash question mark. There we go. And we're done. And that's it. Okay. Let's try it. Let's see if it works. We are going to build it. So we didn't actually use any of these fields because all we're doing is printing it. So I'm going to slap a allow dead code on this, so we don't get those. Cool. All right, we have our build. Let's feed it some data. We're going to run target debug Serde CSV. We're going to feed it data.csv, and we should see beautiful, our deserialized data. I think this is very cool, right? So like our entire parse, it helps that CSV is extremely easy to parse. You just split on new lines and then split on commas, right? We could have done something more fancy with like dealing with quoting and escaping everything. But we have fed a CSV document into this data structure. We did not have to worry anything about how this data structure looks because we just implemented the interfaces that Serde wanted us to do, fulfilling the types that Serde wanted us to fulfill, and we got some data out of it. It's great. We can try other things. Let's try making a instead of a vec, we can make, I don't know, a hash set. Hash sets are sequences, right? I'll make a hash set. We'll import it. We'll make these hash and equal, and partial equal. That's important. Question operator. Oh yeah, this has to be a hash set to serialize. Great. Let's try it. Let's build it again. Let's run it again. And there's our data again. It all worked exactly the same. Our data is in a different order now, right? 3, then 1, then 2, because the hash set is not an ordered container. But a hash set can be deserialized. It knows how to turn a sequence from Serde into a hash set, and everything works out. Let's do some more. Let's try to grab this. Let's try to grab this integer, right? This value. So let's put a value on here. Cool. Let's build this. Oh, I guess you'll also notice too that Serde didn't complain at all. We fed it these two values, and the struct just discarded them, right? This is sort of the default behavior from JSON because they're sort of assuming that if you have a huge quantity of keys in your data structure, you only really care about some of them. There's ways to configure this derive to ask it to not discard unrecognized keys, but that's what it's been doing. So here's our value. Let's try this again. Let's actually build it. Oops. So an error. So this is now where the error side comes in, right? This is an I32, but when we made our very, very simple CSV implementation and we started, way down here, we started feeding data into it. Well, we are turning a string into a deserializer, and a string is not smart enough to turn itself into an integer. A string wants to be a string, and integers do not like deserializing themselves from strings. There's too much that can go wrong. So what are our options? Well, we can make this a string. That would be silly. We could enhance this. We could enhance our CSV to start producing strings. But actually what I'm going to do instead is we're going to put an attribute on this. We're going to say Serde with, and there's a great library here. Use Serde with Rust display. This is basically going to say, all right, this type can be deserialized from a string via fromster, and it can be serialized into a string via display, right? It's just your classic string conversion using string.parse. So we'll put this right here. I think it has to be quoted. So we should now see some integers. There we go. Amazing. I don't know. This really just fills me with delight. Like I love seeing this thing work. One of the reasons that CSV was very easy to do like this is that CSV is not a recursive data format. It isn't like JSON where any JSON object can have any other JSON object and so on and so on and so on. A CSV document is strictly two-dimensional. It is a list of rows, and every row is a list of cells, and so on. With one last thing here, I want to show off the headerless version. I have some weird data here that all these rows are different lengths, right? And there's no headers. It's just a list of lists. Should be fine. Let's give it a try. So instead of using our data struct, we are instead going to do just a vec of strings. Cool. Here's our vec. Still going to do stdin. We're going to not deal with headers this time. New without headers. We are going to build it. We are going to feed it some weird data. And there you go. List of strings. This is our CSV document. How are we doing on time? Oh, we're doing great on time. All right. That is my talk.
Okay, the first one is from Renee.
Okay.
And the question is, I know there are some wire types that include tags for any data types it can have, i.e. BSON, CBOR, and so forth.
Mm-hmm.
How can that be shown in the Serde data model?
It's interesting. So the way that shows up in the Serde data model, it depends on what the tags are expressing. If the tags are expressing like, it's an int or it's a vector or it's a whatever, what we did here is we used to serialize any to say we always know what type of data we have, and we are always going to be feeding you whatever data we have. It would do the same thing, but in a more complex way. In this case, we always knew we had it because a CSV document can only ever have one thing. It's always a vector of something or a sequence of something. But what you would say instead, if you had some kind of tag, let's say like let tag is an integer. So we'll match our tag. I'll say, all right, if it's 0, we have an integer, so we're going to, or maybe 0 is a Boolean. So we'll say visitor dot, we'll read a Boolean and visit a Boolean. And maybe 1 is a signed integer, so we'll say visitor dot visit I32, right? And maybe 2 is a vector of something, so we'll say 2 visitor dot visit sequence, and so on, right? And so our responsibility as the serializer is to pluck the data out of our wire format, turn it into one of these Serde types, and then feed it into the visitor. And then the visitor has said, all right, I know what to do with a bool. I know what to do with an I32. I know what to do with the sequence. Kind of make sense? Cool. Other questions in there?
The second one, I know that you are also a big advocate for nom parsers.
Yes.
So of course, the second question is, how do we distinguish between the times that Serde is the best option and nom is the best option?
Yeah, this is a very, very good question. So they seem very similar, right? They're both dedicated to taking some kind of wire data and turning it into some kind of data structure. But they actually do different things, and often you will have to use them together. Like when you're writing a deserializer, you're going to have to use a parser of some kind if you're not doing something trivial. So looking again at what our interface is here, right? We are deserializing some kind of data, right? Our type has asked us for anything, or it's asked us for an I64 or for an option or for whatever it is it wants to get from us. And we have promised that we are going to give it whatever it wants via this visitor. There is nothing here about parsing, right? We send a bool, like visitor.visitBool wants a Boolean. Excuse me. Visit I32 wants an I32. Visit sequence wants some kind of sequence access, right? Separately, you have to figure out how to parse it. What that looks like in practice is a little more complicated to explain. If I had more time, or if you want to message me separately, I'm happy to show you the one that I wrote a few weeks ago. But basically, you have to write a nom parser that operates on fragments of your data and produces individual pieces of data that you can then feed into these visitor methods, right? They do, even though it feels like they do the same thing, they actually do essentially orthogonal things, right? A parser is about recognizing a particular syntax and turning that syntax into a particular type of structured data. Whereas a deserializer is about abstractly turning something from the Serde data model into any arbitrary Rust type that can be converted from that Rust data model. They work great together, no question, but they do different things.
That makes a lot of sense.
Yeah. It's sort of funny because, again, like this would be our nom, right? Like when I did this for KDL, I have hundreds of lines of nom parsers to parse that thing, because that's a big, like YAML style, white space delimited, node based, right, type data format. CSV is much easier. CSV, you split on new lines, you split on commas, couldn't be easier. But this is our parser, right? This is doing the same thing as num. Like Serde, there's nothing Serde about this. This is a parser that produces iterators of strings that Serde then takes and spits into its data model, and then from there into specific Rust data structures. Make sense?
Thank you.
All right, I see we have 2 minutes to go. It sounded like there was 2 questions in the Slack, so that's probably it.
Yep, no more have been posted.
Okay. In that case, thank you so much, everybody, for coming. Thanks for listening to me go through that. Obviously, feel free to come to me separately with any other questions you might have. I'm happy to talk about it. I'm happy to show off what I wrote several months ago when I was writing one of these for a more sophisticated data format. I'm actually really happy with how it turned out. Yeah, thanks, everybody.